Welcome to this lesson on indirect proof and inequalities in two triangles. And what we're going to start with is this idea of indirect proof, which is a strange concept from what we've been doing with regular proofs, in that you start by assuming that the thing you're trying to prove is false. So indirect proof is oftentimes referred to as proof by contradiction. You're going to assume that what you would like to prove is false and show that that contradicts some rule or contradicts the given, and by doing so that means that your conclusion actually has to be true. So it's kind of a roundabout way of doing a proof, but it's one that's very necessary in proofs. In fact, once you get to college and you're doing proofs in your math classes, it's a common type of proof by contradiction. So that's the idea for what we're going to do today. We'll see a few examples on that, and then we'll talk about comparing sides of and angles between two different triangles. So in writing an indirect proof, four things you got to know. You've got to identify the conjecture to be proven, and then you have to assume the opposite. That's the contradiction part you're looking for. So you're going to assume the other way, and then use direct reasoning to show that that really does contradict some rule, whether it's the given or one of our known postulates or theorems. It contradicts one of those things. If it contradicts that, then our conclusion our assumption that that conclusion is false actually has to be wrong, and therefore if false is wrong, then it must be true. Proof by contradiction. So we're going to do an indirect proof here. We start with a being greater than 0, and we want to show that that means that 1 divided by a must also be greater than 0. Saying a is greater than 0 means a is a positive number. So if a is a positive number, then the reciprocal has to be a positive number. That's what we're trying to prove. So what we're going to do is we're going to assume that if a is a positive number, then the reciprocal is not a positive number, and show that that causes a contradiction. Okay? So we're given that a is a positive number. We're trying to prove that means the reciprocal is positive. So we're going to assume that the reciprocal is not positive. Well, if it's not positive, then either it's 0 or it's negative. So I can take care of both of those by just saying it's less than or equal to 0. So I'm going to assume that the reciprocal is less than or equal to 0. And I'm going to show that that causes a contradiction. So in order to do this, I'm going to take the fact that I'm given that the number a is a positive number, and that I'm assuming that the reciprocal is either 0 or a negative number. Well, what I know then is if I multiply those two together, if a is a positive number and the reciprocal is 0, then you multiply positive times 0, you get 0. And in the second case, if a is a positive number and the reciprocal is negative, a positive times a negative is negative. So if I was to multiply these two numbers together, either I'm going to, if the reciprocal is not positive, I'm either going to get an answer of 0, or I'm going to get an answer that is negative. So we can take care of that by saying that when I multiply them together, I would get an answer that is less than or equal to 0. It's either going to be 0 or a negative number. Here's where the contradiction comes in. We know that when we multiply two fractions, like in this case, the a could be considered a over 1. So if I was to go over here, I could put a little 1 underneath here. Well, then what I know is the a on top and the a on bottom are going to cancel. They're gone, and all I'm really left with is 1. So what I'm saying is, if we have to assume that the reciprocal is less than or equal to 0, then we have to accept that 1 is less than or equal to 0. Well, we obviously know that's false. 1 can't be less than or equal to 0. 1 has to be greater than 0. So if assuming that our reciprocal had to be 0 or a negative number caused 1 to be less than or equal to 0, that's the contradiction we're looking for. Therefore, our reciprocal can't be 0 or a negative number, which means the only logical choice left is that our reciprocal has to be a positive number. So we have proved by contradiction that our reciprocal is positive. I know it's a little strange, but believe me, again, it's a very useful type of proof. Okay, we're going to do another one. This one we're going to prove that a triangle can't have two right angles. So we're going to do a proof by contradiction. We want to prove that it can't have two right angles, so we're going to assume the opposite. We're going to assume that we have a triangle that does have two right angles and see what happens. So here's what we're trying to prove. We know that a triangle's interior adds up to 180 degrees. That's our triangle sum theorem. And we want to prove that it can't have two right angles, so we're assuming that it does have two right angles. So here we go. We're going to say that we've got two of these angles of these three that have to add up to 180 are 90 degrees. So we're plugging in 90 for the measure of angle 1 and 90 for the measure of angle 2. Using a little algebra, we see that what we get is that the measure of angle 3 has to be 0, if that was true. Well, we know a triangle can't be a triangle if one of its angles measures 0. So this can't be a triangle if the two angles are 90 degrees, because one of the angles ends up measuring 0 in your triangle. Therefore, it's not a triangle. We found a contradiction, so we know that we cannot have two angles that measure 90 degrees because that forces the third angle to be 0. So we are able to make our conclusion that the assumption a triangle can have two right angles is false, so we now can say that two right angles cannot exist in the same triangle. Alright, little break from the indirect proof, and now we'll talk about comparing a couple different triangles. We have two theorems that are going to help us with this, the hinge theorem and the converse of the hinge theorem. Basically, here's the way it works. If you have two congruent sides in one triangle, congruent to the two sides in another triangle, and we know something about their included angles. So the angle between the two congruent sides. In the first case, angle A is between the congruent sides AB and AC, and in the second case, angle D between the two congruent sides DE and DF. And they're, of course, congruent across the triangles is what we're talking about. AB being congruent to DE and AC being congruent to DF. If we know that those sides are congruent but the angles are different, and so in this case that the measure of angle A is larger than the measure of angle D, then I know the sides opposite those angles are proportional to the angles. In other words, what I'm saying is if this angle here, angle A, is bigger than angle D, then the side opposite angle A, side BC, is going to be larger than the side opposite angle D. So that we're talking about side EF. So side BC has to be a longer side than EF because angle A measures more than angle D. The side opposite has to be bigger. But this only works when the two sides in one triangle are congruent to two sides in the other triangle, and then I'm focused on the angles that are the included angles for those sides. Those things have to be the same. If I'm just talking about any two random triangles, we can't use these assumptions. So we have to be very careful about making sure that we at least have a couple of congruent sides. That's the hinge theorem. In the converse of the hinge theorem, we have the same process. We still have to have the two congruent sides, just like we did before. But now what I know is instead of knowing something about the angles, I know something about those third sides in each of the two triangles. In the case here in the picture, I know that side GH in the first triangle is actually longer than side KL in the second triangle. And if that's true, then that means the angle opposite GH, which in this case is angle J, has to be bigger than the angle opposite KL, which in this case is M. So angle J has to be bigger than angle M, which is what we see as the conclusion for the converse of the hinge theorem. You may want to pause this slide and take a closer look at it. Make sure you understand what's going on. When you're ready, move on. So here what we want to do is we want to compare the measure of angle BAC and the measure of angle DAC. So what the two angles I'm wanting to compare, BAC and then DAC. So I want to compare these two angles. What I know first and foremost is that on one side of each of those angles I have a set of congruent sides. AB and AD are congruent to each other. But I also know that those two angles share a side. They share side AC, and of course the reflexive property means that side's congruent to itself. So what I have in the first triangle is two sets of sides that are congruent to two sets of sides in the second triangle, and I'm focusing on the two included angles, in this case angle BAD and angle BAC. So what I do is I look opposite those angles. Opposite in the BAC angle is a side of length 7, and opposite the DAC angle is a side length 6. Since 7 is bigger than 6, I know that the angle that the 7 is opposite, BAC, has to be the bigger angle. BAC will be the bigger angle because opposite that angle is the bigger side. So here's where we marked the two lengths of 4 being equal to each other. Here's where we used the reflexive property, and then we made our conclusion. We noticed that BC was bigger than DC, 7 is bigger than 6, and so we're able to make our conclusion using the converse of the hinge theorem. So this is taking us back to look at the angles, that the measure of angle BAC is actually the bigger angle, just like we marked up here. Pause the slide if you need to. Here I want to compare EF and FG. EF and FG are sides. So what I'm focusing on here is I just want to know, is this side or this side the bigger one? I want to know which of those two sides is the bigger side. Well, what I should see is that I have two sides between these two triangles that are congruent. EH and HG are congruent. And there's a shared side, FH. Now if I knew what this angle right here was, then I could compare. Well, what I know is that 82 and that angle form a linear pair. So I can figure out what this angle measures. And I should be able to see that it's going to measure 98 degrees. Okay. So I have a 98-degree angle here. I've got the two congruent sides for this triangle versus the two congruent sides for this triangle, and I'm focused on the included angles. Well, the bigger angle is 98, which means the side opposite the 98 has to be the bigger side, and that means that FG has to be my bigger side. Here, these are the two 7s. This is my reflexive property, that FH is equal to itself. And here I knew that angle EHF, sorry, I'm looking at this and it's stated wrong. Fix that. EHF, the measure of that angle is actually less than the measure of angle GHF. The GHF is the 98-degree angle. Okay, so just ignore what was here before and realize that this angle is actually smaller than the other angle. Okay, and therefore GF is the bigger angle, bigger side. GF opposite the 98-degree angle is greater than EF, or I read the other way, EF is smaller than GF. And that's using the hinge theorem. The hinge theorem is, remember, the one that lets you compare sides. The converse of the hinge theorem lets you compare angles. Okay, pause the slide if you need to. Here I want to know the range of values for K. Now this one gets a little complex, so you're going to want to pay close attention to the calculations we do here. First, you can see that there are two congruent sides, side LP and side LM. And then like before, we have a shared side, side LN. So I've got two sets of sides in the top triangle congruent to two sets of sides in the bottom triangle. So what I do is I want to talk about these two angles. Well, if I look across from the 38, I see a 19. If I look across from the 5K minus 12, I see an 18, a smaller number. So using the converse of the hinge theorem, I know that this angle, the 5K minus 12, has to be a smaller angle than the 38 degrees because it's opposite a smaller side. So I can actually set up an inequality that the 5k minus 12 must be less than the 38 degrees. So I'll set that up, again using the fact that the reflexive property and then the two sides that were marked congruent, and that I can see that Mn is bigger than Pn, okay, which are these two sides over here, the 19 and the 18. That allows me to use the converse of the hinge theorem to make this statement. 5k minus 12 is less than 38. Little simple algebra, add 12 to the other side and divide by 5, and I get that k is less than 10. So I know that first and foremost, k has to be less than 10. But what we have to keep in mind here is there's a lot of numbers less than 10. Let me give you an example. Negative 5 is a number less than 10. If I plug negative 5 in to 5k minus 12, I'd have 5 times negative 5, which is negative 25, minus 12, which is negative 37, and I would be saying that this angle is negative 37 degrees. Well, we can't have a negative angle in a triangle. So I can't just simply say that k is less than 10. If I do, then I'm bringing in a lot of negative angles into this problem. So I have to have a minimum that k can be as well. I have my maximum. K can't be 10 or more. It has to be some number smaller than 10. But it also has to be bigger than some number. And so what I have to keep in mind is that my angle that is being measured as 5k minus 12 has another requirement. It has to be, in order for this to be a triangle, it has to be an angle greater than 0. It can't be 0 and it can't be a negative number. So I should set up 5k minus 12 to be greater than 0 also. And so I know it's got to be less than 10, but 5k minus 12 has to be greater than 0, and I can solve for k that way and create a compound inequality. So 5k minus 12 greater than 0, I'll add 12 to the other side and divide by 5 and get that k has to be greater than, sorry, this slides are a little goofy tonight, k has to be greater than 2.4. 2.4. Okay, so if k has to be greater than 2.4 and less than 10, then I have to have a number somewhere between 2.4 and 10. Combining these two inequalities, this gives me my compound inequality that looks like this. 2.4 is less than k, which is less than 10, is how that's read, which means k is a bigger number than 2.4, but a smaller number than 10. And as long as I pick a value like that for k, then it works with the triangle. Here I want to compare these two angles, and so what I have to do is use my converse of the hinge theorem. So I have to start with what I know is congruent. I start with FG being congruent to HG. Those two sides are definitely congruent, and I know that EG is congruent to itself. And the two angles that I want to compare, EGH and EGF, are these angles, which would be the included angles for those two sets of congruent sides. Okay. So I want to compare these angles. Well, what I do is I just look directly across. Across from angle EGH is a 9, and across from angle EGF is a 10. The one that's got the bigger side across from it is going to be my bigger angle. That's going to be EGF. So EGF is the bigger angle. Here is the two 12s. Here's the shared side. And then I'm looking at those two sides, EF and EH, the 10 and the 9. Using the converse of the hinge theorem. Oops. Sorry about that. Using the converse of the hinge theorem, I see that as what I said, that EGH is less than EGF. Okay. That EGF is the bigger angle. Alright, here I want to compare these two sides, BC and AB. BC and AB are these two top pieces of the triangle. I want to know which one is the longer piece. By now you're probably seeing how this works out, and you probably already can tell that BC is going to be the bigger piece. So if I look at the pieces that are congruent, AD and CD are congruent and they share side BD, and I'm looking at the two angles included between them, 64 and 65. Since 65 is bigger, the side opposite 65, which is BC, has to be the bigger side. These were the two nines. This is the shared side, and then these are the two angles, and I see that ADB, again, some issues with the notation tonight. BDC is the bigger angle. Apologize for the notation problems this evening. And I see that BC has to be bigger than AB. Okay, a little application problem. John and Luke, they're leaving school at the same time. So they're starting at school. Now what John is going to do is John is going to bike 3 blocks west. That would be this way. And then he's going to ride 4 blocks north. So he's going 3 blocks and then 4 blocks. Now what we should notice is that Luke is going to go the same number of blocks. He's going to go 4 blocks east, and he's going to go 3 blocks at a bearing of 10 degrees east of south. I'll explain what that means in just a second. And I want to know who is farther from the school. Well, they both went 3 blocks and 4 blocks, but one of them is further from the school. And so here's what we do. We look at the fact that John went west and then north. West and north would form a 90-degree angle. So what I have to do then is compare that to what Luke did. Luke went east, but then he went 10 degrees east of south. So true south would have looked something like this. He would have headed in this direction. But what he's done is he's actually gone 10 degrees east of that. So he's moved a little bit more to the right than going directly down heading south. So instead of going 90 degrees here, he's gone 90 plus 10 more. That means that this angle right here is a 100-degree angle, not a 90-degree angle. So he's got 100 degrees for his angle versus the 90 degrees that John had. Now everything else about them is the same. They went, Luke went 4 blocks east compared to John's 4 blocks north, and Luke went 3 blocks 10 degrees east of south, while John went 3 blocks west. So those two lengths are the same, and then I'm looking at the angles between them. Well, 100 degrees is more than 90 degrees, so the side opposite that, which is this diagonal distance from the school to Luke's house, has to be bigger than the diagonal distance opposite the 90-degree angle, which represents the distance, the direct distance from the school to John's house. So I know that Luke has to be further away from the school than John does. You can see those calculations right here. Again, you can see where we got the 90-degree angle and the 100-degree angle. And since the 100-degree angle is from Luke's calculation, we know that Luke has to be farther away using our hinge theorem. Okay, we're going to write a 2-column proof. We're given that AB is congruent to CD, and we're given that the measure of ABD, that's going to be this angle right up here, is more than, bigger than CDB. Okay, so the single arc is bigger than the double arc. So what I know in just looking at setting this proof up is that I'll use the reflexive property on BD, and now I've got 2 sides in this triangle, lower left triangle, that are congruent to the 2 sides in the upper right triangle, and I'm looking at the included angles. And I know that the included angle ABD is bigger than the included angle BDC, so I know that side AD is going to have to be bigger than side CB. Wow, we're having some issues tonight. Again, I apologize. I thought I had proofed this better. Obviously I hadn't. So we're trying to prove that AD is bigger than BC. AD. Okay, so going through this proof, we start with our given that AB was congruent to CD and the measure of ABD was greater than the measure of CDB. We then use our reflexive property and then make the statement that AD has to be greater than CB by our hinge theorem. Okay. Pause that if you need to, otherwise we'll move on. Okay. Here I want to write a two-column proof. We're given that C is the midpoint of BD, and we're given that the measure of angle 1 is equal to the measure of angle 2. We want to show that, we're also told that the measure of angle 3 is greater than the measure of angle 4, and we want to show that that means AB has to be greater than ED. So, a few things I want to mark in this picture. C is the midpoint of BD. That means BC and CD have to be congruent. I'm also told that angle 1 is congruent to angle 2. Well, if I look at this triangle in the middle, ACE, these two base angles are congruent, which means this is an equilateral triangle. Now, I can look at that. Remember, we had two different names that we used for this I wanted you to be familiar with. We said that this could be, if the base angles are congruent, the sides are congruent. That's the converse of the base angles theorem, but it's also known as the converse of the isosceles triangle theorem. So you can look at it either way. And so what I have is two sets of sides on the triangle on the left, congruent to two sets of sides on the triangle on the right, and I'm actually comparing angle 3 and angle 4, the two included angles, and I'm told that angle 3 is bigger, which means the side opposite angle 3, side AB, has to be the bigger side. Okay? And that's using the hinge theorem. So we're going to set this up that we have an isosceles triangle. And then we're going to show that those included angles are the angle 3, the included angle, since it's bigger than angle 4, means it's side AB, the opposite side is the bigger side. So we had our given. We used the definition of the midpoint to state that BC was congruent to DC, like you saw. That angle 1 was congruent to angle 2 by the definition of congruent angles. And that meant that sides AC was congruent to EC. Converse of the isosceles triangle theorem, also known as the converse of the base angles theorem. So either one of those is fine to use. And then that let us use the hinge theorem to state that AB was greater than ED. If you need to, go back and look at the picture and look at the proof, see how it all comes together. We talked it through, so these are just the formal steps. I want to prove in this triangle that since I know SRT is congruent to STR, the two red angles are marked there, and I know that TU is greater than RU, that implies that angle TSU, which is the angle here, is bigger than angle RSU, the angle here. So what I'm going to start with is that I have this triangle, TSR. TSR has two congruent angles in it. These would be the base angles. Well, converse of the isosceles triangle theorem, or converse of the base angles theorem, however you want to call it, tells me that ST and SR would have to be congruent. So that's good to start with. And then I know that SU, this whole segment here, is congruent to itself. Okay. So what I now have is a triangle, full triangle on the left versus full triangle on the right. I have two sets of congruent sides and the included angles, and I was told that TU is the bigger side. Well, the angle opposite TU is angle TSU, so it has to be the bigger angle. So it's easy to see that what we're trying to prove is true. Now we just need to make the steps. So we start with our given. Identify that ST had to be congruent to SR by the converse of the isosceles triangle theorem. Again, you could also say that's the converse of the base angles theorem. Then we used the reflexive property to state that SU was congruent to itself, which then allowed us to use the converse of the hinge theorem in order to state that the measure of angle TSU had to be greater than the measure of angle RSU. Okay. You have a quiz that I need you to bring to class, so pause the slides as you need to. This is page 1 of the quiz. Slide 2 of the quiz. And slide 3 of the quiz. Please bring all that to class with you tomorrow. Thanks for listening and watching, and have a great day.